Last lecture, we developed the concept of conservation and derived the expression for conservation of energy. This lecture, we're going to introduce the concept of momentum and derive an expression for another type of conservation of momentum. Momentum will help us determine which way the wreckage goes when two bodies collide. It'll also help us understand rocket propulsion. Yeah, you'll be doing a little bit of rocket science this lecture. If you remember, we built up to work and all the forms of energy we developed last lecture by starting with force and Newton's second law. We're going to use Newton's second law as our launch pad again, but this time we're going to derive an expression for momentum. So we can move mass inside the derivative here because it's constant. So sum of the forces is equal to d dt ma or mb. This quantity mv is the momentum. It's that simple. We're done. So momentum is p. It's a vector quantity, and it's equal to mv, the mass times the velocity of a particle. The greater the speed and mass of a particle, the greater its momentum. As with every vector quantity we've come across, we can talk about momentum in component form as well. So you can have momentum in the x direction, and that's just the mass times the x velocity. And you can have momentum in the y direction, mass times the y component of velocity, and z if you got it. Mass times velocity in the z. The units of momentum are mass times velocity, so kilograms, meters per second. We can write Newton's second law in terms of momentum if we want, and this is actually the way that Isaac Newton himself first wrote down his second law. So it would go like this. Sum of the forces is equal to dp dt, the change in the momentum over time. So this means that the net force on a particle is equal to how fast the particle's momentum is changing. All right, so next we're going to talk about the impulse momentum theorem. And it's going to be kind of similar to work energy theorem. And we'll talk about how they're similar, how they're different, and try to keep them both straight in our head. So when we first introduced work, I'll go to a new color here. When we first introduced work, we said work is equal to a force through a distance, right? Remember, work equals F dot S. Well, now we're going to do something very similar and define a term for a force through time. So we're going to call this quantity impulse, and it's going to be denoted by the symbol J. So capital J is impulse, and it's going to be F times delta T. So work is when a force acts through a distance, and impulse is when a force acts through time or over a time interval. The units for impulse are Newton seconds, because the units for force are newtons and T is in seconds. But alternatively, you can use the same units as momentum, kilograms meters per second, because the units of force are kilograms meters per second squared. And so if you multiply by another seconds, then you cancel out one of the seconds. So the units are the same. And so if we plug in our expression for Newton's second law in terms of momentum, we get the impulse momentum theorem. And it is this. J, impulse, is equal to P2, the momentum at point 2, minus P1, the momentum at point 1. So the impulse momentum theorem says the change in momentum of a particle during a time interval equals the impulse of the net force that acts on the particle during that interval. Now, I remember when I was first learning all this, and I don't know about you, but to me it all sounded a little bit abstract and confusing. I could say it out in words just fine, but to understand what it really means is a little bit difficult. So I didn't get it. So let me see if I can help those of you that are saying, huh, right about now, like I was. So with work and kinetic energy, and the work energy theorem, it's all about forces acting through a distance. With impulse and momentum, and the impulse momentum theorem, it's all about forces acting through time. That's really all that it is. Work is to impulse, as kinetic energy is to momentum. The impulse momentum theorem is the tiny version of the work energy theorem. Likewise, the work energy theorem is the distance-y version of the impulse momentum theorem. If you remember, we've conveniently stopped talking about time as a quantity for the past couple chapters. Well, now with the impulse momentum theorem, we can handle forces acting through a time interval again without having to go all the way back to our constant acceleration equations. So you use whichever one is appropriate, and this gives us new tools to handle time-based phenomena. Alright, that's it for this video.